The Magic of Reality by Richard Dawkins. Picture yourself gazing up at a rainbow stretching across a storm-darkened sky. That perfect arc of impossible colors takes your breath away, doesn't it? For thousands of years, humans spun stories to explain this wonder. The ancient Norse imagined it as a shimmering bridge the gods used to visit Earth. Jewish and Sumerian traditions saw it as heaven's promise after the Great Flood. Beautiful tales, all of them. But here's the thing, there's another kind of magic at work here. A magic that doesn't live in myths or legends, but in the thrill of discovering what's actually happening. A magic that, once you grasp it, leaves you more awestruck than any story ever could. Welcome to the Magic of Reality. We're about to embark on a journey with Richard Dawkins, one of the sharpest scientific minds alive. His book, The Magic of Reality, has mesmerized readers worldwide because Dawkins doesn't just hand you answers on a silver platter. He shows you how we figure out what's genuinely true. Dawkins himself is quite the character. An Oxford professor who revolutionized our thinking with the selfish gene, he took on a different mission with this book, sharing the stunning beauty of science with young minds everywhere. He approaches his subject like a detective, gathering clues from every corner of knowledge to solve the mysteries of our universe. Over the next while, I'll distill the essence of this remarkable book for you. We won't simply learn that the universe is 13.8 billion years old. We'll discover how a rainbow can whisper its age to us. We won't just hear that we evolved. We'll journey backward through 185 million generations to shake hands with our fishy great-great-great-grandparent. Here's my promise. By the time we're done, you won't just possess a collection of scientific facts. You'll have the tools to think like a scientist, and you'll realize that the real world sparkles with more magic than any fairy tale ever dreamed up. Let's kick things off with a question that sits right at the center of our adventure. What is real? Seems straightforward, right? You know the chair supporting you is real because you can feel it. The light illuminating your space, the sound of my voice reaching your ears. Your five senses constantly reassure you that these things exist. But what about the invisible? What about a bacterium so tiny your naked eye can't spot it? Or a distant galaxy, so far away its light has been traveling for millions of years just to reach us tonight? We know they're real, but only because we've invented special tools, microscopes and telescopes, extend our senses where our biology falls short. We understand how these instruments function, so we trust what they reveal. This is your first step into understanding reality. We can know things directly through our senses or indirectly through instruments that amplify those senses. But Dawkins reveals a third, even more powerful method for discovering what's real, especially when dealing with things forever beyond direct observation, like the interior of an atom or the story of how we came to be. This method lies at the very heart of science itself, creating a model. Now, a model isn't just wild guessing. It's a carefully imagined explanation for how something might work. Take Gregor Mendel, a 19th-century monk who wanted to understand how traits passed from parent pea plants to their offspring. He never laid eyes on a gene. Nobody had, but he constructed a model in his mind, invisible units of heredity, and used it to make predictions. He calculated that if his model was correct, he should count 3 times as many smooth peas as wrinkly ones in a specific experiment. When he actually counted them, that's precisely what he found. His model, born purely from imagination, had successfully predicted something in the physical world. This is science's heartbeat. Imagine a model, test its predictions, and if they fail, you modify or discard the model. If they succeed, your confidence grows that your model captures a slice of reality. Which brings us to the other essential word in our title, magic. Dawkins explains there are 3 varieties. First, supernatural magic, the fairy tale kind, where witches transform princes into frogs. We all recognize this as fantasy. Second, stage magic, the dazzling illusions conjurers perform. We know it's trickery, a clever deception of our senses, but it's real in that something genuinely entertaining is unfolding before us. But the third kind matters most. Dawkins calls it poetic magic. It's that sensation of wonder when you look up at a sky packed with stars on a crystal-clear night, or those goosebumps triggered by a hauntingly beautiful melody. It's being moved by something profound and beautiful. The entire purpose of this book is demonstrating that reality, the world understood through science, overflows with this poetic magic. And it's all the more wonderful because it's real, and we can understand the mechanisms behind it. So let's put these tools to work and tackle one of the grandest questions imaginable. Who was the first person? For millennia, every culture crafted its own origin myth. A Tasmanian tribe told of a god named Moini, who tumbled from the stars and, in his dying moments, created humans. But he was in such a frantic rush that he forgot to give them knees and accidentally attached kangaroo tails, leaving them unable to sit. Only when another god, Dromardiner, took pity on them did he fix their knees and slice off those awkward tails. The ancient Hebrew story describes a god forming the first man, Adam, from dust, then crafting the first woman, Eve, from one of Adam's ribs. Norse Vikings believed the first man and woman were carved from two tree trunks discovered on a beach. Wonderful stories, all of them. But what does reality actually tell us? Here's the surprising scientific answer. There never was a first person. Sounds bizarre, I know. But think it through. Every person who's ever lived had parents. And those parents were people too. And they had parents who were also people. You can trace back through your grandparents, your great-grandparents, your great-great-grandparents, and you'll never find a generation where a non-person suddenly gave birth to a person. So how did we get here? Dawkins invites us to try a brilliant thought experiment. Imagine you've got a photograph of yourself. Now stack a photo of your father on top, then his father, then his father's father, and keep going. Stack these photos of your direct male ancestors one after another. How far back do we need to go? Let's travel back 185 million generations. It's an impossible stack to visualize. If each photo was postcard-sized, the pile would tower over 40 miles high. So let's lay them out along an incredibly long bookshelf instead. At one end sits your picture. At the far end, 40 miles distant, is the picture of your 185 million greats-grandfather. What does he look like? A caveman? An ancient bearded sage? Not even close. Believe it or not, your 185 million greats-grandfather was a fish. Now here's the crucial part. If you walked along this 40-mile bookshelf, examining each photo individually, you'd see no sudden transformations. The person in photo number 50,000 would look nearly identical to his father in photo number 50,001. Every creature in the line belongs to the same species as its parents and children. Yet when you step back and survey the entire 40-mile journey, you see a human at one end and a fish at the other. How's this possible? Because evolution is a process of incredibly gradual change, unfolding across immense stretches of time. It's like your own life. You were once a baby, and someday you'll be elderly. But there's never a single morning when you wake up and declare, "Yesterday I was a child, but today I'm a teenager." The change creeps along so slowly it's invisible day to day, yet undeniable over a lifetime. Evolution works the same way. No fish-like creature ever birthed a reptile. No ape-like creature ever birthed a human. Each step was microscopic. But with millions upon millions of generations, those tiny steps accumulate to transform one kind of animal into something completely different. How do we know this isn't just another story? Two powerful evidence streams confirm it. First, fossils. Fossils are the stony remnants of ancient life, showing us snapshots from this long journey. We can even date them using radioactive clocks in the rocks, like the isotope uranium-238, which decays into lead at a known steady rate. These clocks let us place our ancestors on a timeline. Fossils reveal that about 6 million years ago our ancestors were apes, living in Africa. Journey back 63 million years, and they were small, lemur-like creatures. Travel back 340 million years, and they were amphibians, somewhat like newts. Further still, we find our fish ancestors. The second, even more compelling line of evidence lives within our own bodies, our DNA. DNA is the instruction manual for building a living creature, written in a 4-letter chemical alphabet. Turns out, all living things, humans, chimpanzees, mice, even bananas, use exactly the same genetic code. We're all written in the same language. We can compare different creatures' DNA to see how closely related they are. For example, there's a gene called FOXP2, over 2,000 letters long. A chimpanzee's version of this gene differs from ours by only 9 letters. A mouse's version differs by 139 letters. This pattern holds across thousands of genes. It tells us with mathematical certainty that chimpanzees are our very close cousins, while mice are more distant relatives. And the most wonderful part? We share some genes, recognizably the same, with every living thing on Earth. Your family tree doesn't just include your grandparents and great-grandparents. It includes chimpanzees, mice, iguanas, dandelions, mushrooms, and bacteria. Every last one of them is our cousin. That, Dawkins argues, is far more wonderful than any myth. And we know with certainty it's literally true. This brings us to our next big question. If we all share a common ancestor, why are there so many different kinds of animals? Why didn't life just remain as one thing? To explain this, Dawkins uses another wonderful analogy, the evolution of languages. Think about it. Languages like Spanish, French, and Italian are quite similar. They're known as the Romance languages because they all descended from one common ancestor, Latin, the language of ancient Rome. How did one language become many? Imagine 2 groups of people who originally speak the same language but get separated by a mountain range or an ocean. Over centuries, their languages will drift apart. Small changes in pronunciation and vocabulary accumulate, generation after generation. After enough time passes, the 2 groups can no longer understand each other. Their single language has branched into 2. Species do exactly the same thing, and the key ingredient for this branching is separation. Dawkins points to the Galapagos Islands, which famously inspired Charles Darwin. These volcanic islands, relatively young, sit hundreds of miles from the mainland. At some point long ago, a few land iguanas must have rafted across the ocean from South America, perhaps on a mat of uprooted trees, just as was witnessed happening on another island in 1995. Once on the Galapagos, these pioneer iguanas were isolated. Their gene pool, the total collection of genes in the population, was now separate from the mainland population. Over many generations, they evolved to suit their new, harsh volcanic environment. But the story continues. The Galapagos is a chain of islands. Occasionally, a few iguanas would raft from one island to another. These island hoppings were rare enough that populations on each island had time to evolve in their own separate directions. Just as Latin drifted into French on one side of the mountains and Italian on the other, the ancestral iguana population drifted into different forms on each island. Eventually, they became so different that even if they met again, they could no longer interbreed. They'd become separate species. Today, 3 distinct species of land iguana exist on the Galapagos. And in a spectacular evolutionary twist, one population even adapted to life in the sea, becoming the world's only marine iguanas, which feed on seaweed. This process, repeated over and over for billions of years, created the magnificent diversity of life we see today. It's all driven by the engine Darwin discovered, natural selection. It's not just random drifting. In any environment, some individuals have traits making them slightly better at surviving and reproducing. Their genes are more likely to pass on. This process, repeated generation after generation, nudges evolution towards survival. It builds bodies skilled at surviving, whether that means the sharp teeth of a lion or the camouflage of a leaf insect. Every living creature you see is an intricate machine, sculpted by natural selection for one purpose: passing on the genes that made it. So we've explored our own origins and life's rich tapestry. Now let's zoom in much closer and ask, what is everything actually made of? The ancient Greeks proposed that everything was made of 4 elements: earth, air, fire, and water. But one thinker, Democritus, had a more radical idea. He suggested that if you keep cutting something into smaller and smaller pieces, you'd eventually reach a particle so small it couldn't be cut any further. He called this an atom, from the Greek word atomos, meaning uncuttable. Democritus was astonishingly close to the truth. Everything is indeed made of atoms, but we now know there are about 90 different kinds of naturally occurring atoms, which we call elements, things like hydrogen, oxygen, carbon, and iron. Most things we see aren't pure elements but compounds, where atoms of different elements join together to form molecules. Water, for instance, is hydrogen oxide, one oxygen atom joined to 2 hydrogen atoms. Sometimes these atoms arrange themselves in a highly ordered repeating pattern, like soldiers on parade. This is what we call a crystal. A diamond is a giant crystal made of nothing but carbon atoms, arranged in a perfect 3-dimensional grid. But here's where reality gets truly strange. If we built a scale model of that diamond crystal, and we represented the nucleus of each carbon atom with a football, how far away do you think the next football would be? A few feet? 100 yards? The answer is over 15 kilometers, or about 9 miles. Think about that. Even the hardest substance we know, a diamond, is almost entirely empty space. The same holds true for the rock beneath your feet, the chair you're sitting on, and your own body. We're all mostly empty space. So why don't we just fall through the floor? Why can't we walk through walls? Because what we feel as solid isn't the matter itself, but the powerful forces acting between the atoms, holding them in a fixed structure. It's these invisible fields that give the world its feeling of solidity. Now let's dive even deeper, inside the atom itself. For a long time, the atom was thought to be the smallest thing, but we now know that atoms have an internal structure. At the center sits a dense nucleus, containing particles called protons and neutrons. Whizzing around the nucleus are much smaller particles called electrons. The number of protons in the nucleus defines what an element is. An atom with 1 proton is always hydrogen. An atom with 6 protons is always carbon. An atom with 82 protons is always lead. This is why you can't cut an atom of lead any smaller and still have lead. If you managed to knock a proton out of its nucleus, it would cease being lead and become a different element altogether. And what are protons and neutrons made of? Even smaller particles called quarks. But here, Dawkins says, we reach the edge of what can be easily explained. We're entering a wonderland of mystery, where our everyday understanding of things and space begins to break down. Having explored the incredibly small, let's now turn our gaze outward to the vastness of the cosmos and ask 2 questions that have dominated human curiosity forever. Why do we have night and day, and winter and summer? And what is the sun? The illusion that the sun moves across the sky is one of the most powerful we experience. It feels like we're stationary, and the sun is making a daily journey from east to west. But, as you know, it's an illusion of relative movement. Like when you're on a train, at a station, and the train next to you starts moving. For a moment, it feels like you're the one moving backward. The daily cycle happens because the Earth spins on its axis, like a top, once every 24 hours. We're the ones moving, turning to face the sun for day, and turning away from it into our own shadow for night. But what about the seasons? Many people think it's because the Earth is closer to the sun in summer. A simple fact proves this wrong. When it's summer in the northern hemisphere, it's winter in the southern hemisphere. An Australian might be having a Christmas barbecue on a hot beach, while someone in Canada shivers in the snow. They can't both be closer to the sun. The real reason for seasons is that the Earth's axis is tilted, Imagine a rod running through the Earth from the North Pole to the South Pole. This rod isn't straight up and down relative to our orbit around the Sun. It's tilted at an angle of about 23.5 degrees. This means that for part of the year, the northern hemisphere tilts toward the Sun. The Sun's rays hit it more directly, and the days are longer. This is our summer. 6 months later, as the Earth continues its orbit, the northern hemisphere tilts away from the Sun. The Sun's rays hit it at a shallower angle, spreading their energy over a wider area, and the days are shorter. This is our winter. This brings us to the Sun itself. For most of history, we worshipped it as a god, a chariot of fire, or a cosmic egg. But what is it really? The Sun is a star. It's no different from the billions of other stars you see at night, except for one crucial fact. It's incredibly close to us. To give you a sense of scale, if the Sun were a football, the Earth would be a tiny peppercorn about 25 meters away. The nearest other star, Proxima Centauri, would be another slightly smaller football, 6,500 kilometers away. Stars are different from planets because they're massive enough for their own gravity to create immense pressure and heat at their core. When the temperature gets high enough, millions of degrees, a star ignites, becoming a colossal nuclear furnace. It starts fusing hydrogen atoms together to make helium, releasing the vast amounts of energy we see as light and feel as heat. The Sun, and every other star, is the powerhouse of its system. It's the ultimate source of nearly all energy for life on Earth. Plants capture sunlight and use its energy to create sugars. Herbivores eat the plants, carnivores eat the herbivores, and at every step, that original solar energy passes along the chain. The energy powering your muscles as you walk, the heat from a wood fire, even the power from fossil fuels like coal, all of it is just stored sunlight, captured by plants millions of years ago. And this leads us to the grandest question of all. We know what the Sun is, we know what the Earth is, but when and how did all of it begin? The answer, incredibly, lies hidden in a rainbow. As we learned, Isaac Newton showed that white light from the Sun isn't pure, but is a mixture of all the colors of the spectrum. A prism, or a raindrop, can bend this light and splay the colors out for us to see. In the 19th century, scientists developed an instrument called a spectroscope, which is like a very precise prism. When they pointed it at light from our Sun or other stars, they saw something amazing. The spectrum wasn't a smooth, continuous rainbow. It was crossed by a pattern of thin, dark lines, like a barcode. It turned out that these barcode lines are the unique chemical fingerprints of the elements. Sodium has one pattern, hydrogen has another, iron another still. For the first time, we could look at a distant star, millions of light years away, and know exactly what it was made of, just by reading its barcode of light. But then, in the 1920s, astronomer Edwin Hubble noticed something even more profound. When he looked at light from distant galaxies, he saw the familiar barcodes of elements like sodium and hydrogen. But the entire barcode pattern was shifted toward the red end of the spectrum, and the farther away a galaxy was, the greater its red shift. What did this mean? It's something called the Doppler effect, which you've experienced with sound. When an ambulance speeds past you, the pitch of its siren seems to drop as it moves away. The sound waves are being stretched out, making the wavelength longer, which our ears hear as a lower pitch. The red shift is exactly the same effect, but with light. Red light has a longer wavelength than blue light. The fact that light from distant galaxies is red-shifted means their light waves are being stretched. And the only way for that to happen is if those galaxies are rushing away from us at incredible speeds. Hubble discovered that the entire universe is expanding. And if it's expanding, that means in the past it must have been smaller. So scientists did the logical thing. They ran the film backward. They calculated how long it would take for all the galaxies, rushing away from each other now, to come back together to a single point. The answer they found is that everything, all matter, all energy, even space and time itself, exploded into existence from an infinitesimally small hot point between 13 and 14 billion years ago. This was the Big Bang. The story of the universe, and our place in it, began in that singular, spectacular moment. So here we are, on a small, rocky planet, orbiting a medium-sized star, in a quiet corner of one galaxy among billions. We know how the universe began. We know the story of our evolution. But one question remains, a question that fuels our science fiction and our deepest curiosity. Are we alone? This is one of the few questions in the book where Dawkins admits that nobody knows the answer for sure, but science can help us make an educated guess. First, how many planets are there? Until recently, we only knew of the planets in our own solar system. But using clever techniques, like measuring the tiny wobble a planet's gravity causes in its star, astronomers have now detected thousands of planets orbiting other stars. Given that there are something like 10,000 billion stars in the observable universe, the number of planets is almost certainly staggering. But how many of them could support life? Scientists look for planets in the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist, which we believe is essential for life as we know it. We're already finding planets that fit this description, like one orbiting a star called Gliese 581. If life does exist out there, what might it look like? Science fiction often gives us bug-eyed monsters, but Dawkins suggests that the fundamental pressures of evolution might lead to some familiar solutions. For example, light travels in straight lines. Anywhere there's a star, there will be light, and using light to form images is an incredibly useful way to navigate the world. It's no surprise that eyes have evolved on our planet at least 40 separate times. So it's not just a failure of imagination to think that aliens, if they exist, might very well have eyes. This brings us to our final question, and perhaps the most personal one. Why do bad things happen? Why do earthquakes destroy cities? And why do good people get sick? Many myths try to answer this by blaming cosmic mistakes or the sins of our ancestors. The scientific answer is more profound and, in its own way, more comforting. The universe, Dawkins explains, simply doesn't care about us. An earthquake happens because tectonic plates shift. It has a cause, but not a purpose. It's not a punishment. It's not unfair. It just is. Good things and bad things happen to everyone, not because of some cosmic justice, but because things happen. However, there is one area where the world is out to get you, and that's in the realm of biology. If you're an antelope, a lion is actively working for your downfall. If you're a human, a virus is evolving to bypass your defenses. This is the reality of the struggle for existence that Darwin described. Life isn't indifferent. Your enemies, your predators, your parasites, your competitors, have been shaped by natural selection to succeed at your expense. This constant battle is the engine of evolution, a process of incredible creativity, but also one of immense suffering. And so we arrive at the end of our journey, back where we started, with the question of miracles. What should we think when someone claims that a statue wept, or that a ghost appeared, or that water was turned into wine? The 18th century philosopher David Hume offered a simple, powerful tool for thinking about this. He said we should always ask ourselves, what's more likely? Let's take the famous miracle at Fatima, Portugal, in 1917, where a crowd of 70,000 people supposedly saw the sun dance in the sky. What's more likely? 1. That the sun, a gigantic ball of nuclear fire 1,000,000 times the size of Earth, actually broke from its position, hurtling toward a small town in Portugal in a way that would have ended all life on our planet, and then returned to its normal place. Or 2, that a group of people, staring at the sun on a cloudy day, something that can damage your eyes and cause visual distortions, experienced a shared illusion, a story which was then exaggerated and spread as a rumor. Hume's point is that, however unlikely the second option seems, it's vastly more likely than the first. A story being misremembered or exaggerated is common. The laws of physics being shattered is not. This is the ultimate magic of reality, We don't need to invent supernatural stories to explain the world. The real explanations, discovered through the patient, brilliant work of science, are more beautiful, more elegant, and more awe-inspiring than any myth could ever be. Science doesn't take away the wonder, it adds to it. It gives us a universe far grander than our ancestors could have dreamed of, and it invites us to be part of the magnificent quest to understand it. The truth, as Dawkins shows us, has a magic all its own. What I love most about the magic of reality is that it's not just a book of answers. It's a book that teaches you how to ask questions. It hands you a toolkit for thinking, a way to navigate a world full of misinformation, ancient myths, and modern rumors. Dawkins' central message is one of empowerment. You don't have to take anyone's word for it. You can look at the evidence, test the ideas, and come to understand the world for yourself. The most powerful lesson, for me, is the idea of poetic magic. For centuries, there's been this false battle between science and wonder, as if explaining something destroys its beauty. Dawkins argues the complete opposite. Understanding how a rainbow works, knowing that it's made of sunlight being split into its constituent colors by millions of tiny falling raindrops, doesn't make it less beautiful. It makes it more beautiful. It connects you to the deep and elegant laws of physics that govern the entire universe. It transforms a fleeting spectacle into a moment of profound connection with reality. So how can you start applying the ideas from this book today? It's simpler than you might think. Here are a couple of small actions. First, practice asking Hume's question. The next time you hear a sensational story, an urban legend, or a claim that seems too good or too strange to be true, pause and ask yourself, what's more likely? Is it more likely that the laws of nature were suspended, or that someone is mistaken, or that the story has grown in the telling? This simple mental habit is a powerful filter for truth. Second, actively seek out the poetic magic in the world around you. The next time you look up at the moon, don't just see a light in the sky. Remember that it's a massive sphere of rock, held in orbit by the same force of gravity that keeps your feet on the ground. The next time you see a tree, don't just see leaves and branches. See a solar-powered factory, turning sunlight into life itself. By consciously connecting everyday things to their deep scientific explanations, you can start to feel that sense of awe that Dawkins talks about. You can find magic not in escaping reality, but in diving deeper into it. That was a summary of The Magic of Reality by Richard Dawkins. We've explored some incredible ideas today, but a summary is like looking at a map of a beautiful country. The map can show you the landmarks and the main roads, but it can't give you the feeling of walking through ancient forests, climbing mountains, or meeting the people. The real magic happens when you explore it for yourself. This book is an invitation to do just that. If any of the ideas we've talked about today have sparked your curiosity, I truly encourage you to pick up a copy. Reading it isn't just about learning facts. It's about changing the way you see everything and discovering the profound, poetic magic hidden in the world all around us. The link to the book is in the description. Also, if you found this journey valuable, please show your support by liking this summary and subscribing to Billionaire's Bookshelf. That way, you won't miss our next exploration into another life-changing book. Let's keep learning and growing together.